Greetings, ma'am. This is Yashesh Singh and Rohan Kirdar from Division D, second year. So today we will be going to present a presentation on advanced smart parking management system using data structures and real-world simulations. So the overview of the smart parking system is based on real-world simulation using Python and efficient slot management and vehicle tracking. So experience a dynamic simulated parking environment designed to mirror real-world complexities and challenges. Our system leverages advanced data structures to optimize parking slot allocations, minimizes search times, and provide accurate real-time tracking of vehicles within the facility. There are various problems during smart parking system. So some of them are increased demand for structured parking. Rapid urbanization and a growing vehicle population are leading to an escalating need for efficient and organized parking solutions in metropolitan areas. Key operational challenges: slow slot allocations, VIP handling, overflow management, and lack of navigation. A critical need for a scalable system. There's an urgent requirement for a system that is scalable, fast, and organized to address these issues, improving user experience and operational efficiency. So, our system architecture overview for the smart parking system is array, hash map, queue, priority queue, graph, and binary tree. So, array fundamental for storing ordered collections and basic indexing. Hash map essential for rapid lookups and efficient mapping of parking slots to vehicle data. Priority queue is manages VIP access and prioritize slot allocation effectively. Queues handles vehicle entry and exit sequences, ensuring fair flow management. Graph models the parking lot for optimal pathfinding and navigation. Binary tree optimizes search operations for available parking spaces within zones. So we have used our array parking slots. So the above code stores which vehicles occupies which slot. So access enables constant time access to any parking slot status, ensuring quick updates queries in real time. Mirror real parking slots. Numbering provides a direct and intuitive digital representation of the physical parking lot layout.
Okay, so hello, ma'am. Myself, Rohan Kidat, and I'm going to explain you about the data structure we use in the code. So the first one is the dictionary, also called as hash map. Uh, we have used hash map for slotting vehicle and mapping its location, so the user can be able to access and find out its vehicle from the parking very easily. And the second one is the priority queue. We have used the priority queue for VIP vehicles. If any VIP vehicle is registered in our app, so it will be the first one, or it will get a priority to be in the queue as a priority. And the third one is the queue for waiting line, also called as a DQ. When suppose if the slots are full, then a vehicle can be put in the waiting list for its next turn, so that it will be book its slot for waiting, and it will be accessed once the slot in the parking is freed. And the next one is the graph. The graph is used to design or to show the user its working parking place, so that he or she will get a brief idea about the location, lane, where to park and where not to park. And the and one of the data structure is the binary tree, which shows the vehicle log history, like the timing, the lane, in short, the whole history about the parking and the car. And the final conclusion of our project is to make user efficiently and user friendly use our app, and so that there will be no headache for him in future for finding parking places. And that's all. Thank you.
Thank you, ma'am.
Thank you.
So, good morning, everyone. Today, me and Mohit are going to present our data structures IA2 project, which is a call center management system. This project shows how different data structures can be combined to efficiently manage a call center. So I will be explaining some slides and then Mohit will be continuing the rest. So the problem definition, the main problem we are solving is managing the workflow inside a call center. Many tasks happen together. Callers join queues, agent take calls, calls get logged, and history must be maintained. To handle all this, we use different data structures. So we use queues to store waiting callers, lists to manage available agents, and again lists to store completed call logs, and stacks to keep recent call history. Using three structures together, we make the system organized, fast, and scalable. Third is the appropriateness of these data structures. So each structure we selected has a specific purpose. So queues are used for VIP and regular callers, like as per queue uses FIFO structure order, and it ensures fairness while still giving priority to VIPs. Stack is used to store recent call history, as I mentioned above. It follows LIFO, so the most recent call is always on top. And third is the doubly linked list. So it is used to manage agents. Since agent can change status anytime, this structure allows easy forward and backward movement. So fourth one is the implementation details or the code we have wrote for this. So in implementation, we created a central structure called call center, which stores all our queues, stacks, and lists. So we have just taken a part of the code. The system works using an event-driven approach. So when a new call comes, it is added to the correct queue. When an agent becomes free, the system automatically assigns the next call. VIP calls are always checked first, and memory is allocated and freed properly to avoid leaks. So the overall logic ensures smooth operation just like the real call center. For the further explanation, I would like to hand it over to Mohit. Thank you.
So, hello, ma'am. To ensure our call center management system is robust and function correctly, we develop a set of comprehensive test cases. So first, we have validated basic end-to-end flow. A call being received, successfully assigned to an agent, and then properly ended. Next, we concluded a VIP priority test. This was crucial to confirm that a call marked as a VIP bypasses the regular queues for immediate assignment, which is core feature of our design. We also ran a regular FIFO queue test, which stands for first in, first out. This test confirmed that a non-VIP caller are handled in exact order they call in. Finally, we tested error handling for invalid operation to make sure our system doesn't crash and respond gracefully to an unexpected output. Now moving to the next slide, result analysis. You can see direct screenshot from our you can see direct screenshot from our result analysis. This demonstrate a successful run of the VIP priority test we just mentioned. You can see the console menu with all the system operations, all the system also. The first one is a receive the call, end a call, transfer a call, showing the waiting queues. Fourth is the showing recent call history. Fifth is list all agents, and if you want to add a new agent to handle the calls, we can do it. And fourth and last one is the exit, which exit the console menu with all the system option. We selected option one, receive a new call. We entered Om as the caller ID and Mohit as the issue. Crucially, when prompted, is this a VIP call or a priority call? We enter Y for yes. The system immediately identify it as a priority call, and because an agent was free, it assigned call Om to agent 001, proving and our priority queue logic works perfectly. Moving to the parallelism report of our project, the our project plagiarism report shows a similarity index of 12%, which confirms the originality of our implementation and documentation. For the reference we used for our project, we consulted a YouTube video to help understand some of the basic data structure used in our implementation. We also refer some tech channels for our data structure understanding like Gate Smasher and Code with Harry. Lastly, in the conclusion, we have developed a menu-driven project of call center and implemented some basic logics which are performed in the call center using doubly linked list, stacks, queues, priority queues. Thank you. The presentation, Yashesh and Rohan. So, how well do you think this system would improve the overall parking experience in the busy city?
I think it would greatly reduce confusion, save time, and make parking more organized.
So, which
Okay.
feature of this smart parking system stood out the most of you?
The time management system and the priority queue are the two features that I like the most and which are most essential for our program project.
So, do you feel this solution can be realistic in and adopted in malls and offices
Yes,
or
it
in
is.
campus?
Yes, it is scalable and realistic for all these places.
What challenge in real life parking do you think this system solves best?
This system solves the headache of finding a place for parking, and it makes a person really easy to get its slot booked.
Would you prefer a system that prioritizes VIPs or one that treats all vehicles equally?
A balanced approach with necessary VIP priority works best.
If you were to upgrade this system further, what feature would you add?
A mobile app with real-time updates and navigation will be the most valuable upgrade, I guess, for it.
Okay.
Thank you.
Thank you, Yashesh and Rohan.
Thank you.
Thank you. To Mohit and Om for your presentation on call center management. So now I and Rohan will be asking you some questions regarding it. So you define the system as using both a list for all call records and a stack for recent call history. Why use both? Don't they do the same thing?
So they serve two different purposes. The list is for historical tracking. It's the complete permanent archive for reports. And the stack is for quick reference. So it's a LIFO structure which is logical for showing most recent history.
Okay, so why did you use queues to hold waiting callers and not stacks?
So we use queues because they are first in, first out, which is the ideal and fair model for waiting line. The stack would be last in, first out, meaning the last caller would help first, which would be unfair system.
Why did you use two separate queues for VIP and regular callers instead of a single, more complex priority queue?
So using two separate queues is a simple and effective way to handle priority. Our system just checks the VIP queue first and only checks the regular queue if the VIP one is empty. This gives us the priority we need and avoids a complex priority queue.
And so, for callers' experience, when I call into your system, what's the first data structure I interact with, and how does it ensure that I am treated fairly?
So you interact with a queue. This ensures fairness because a queue follows first in, first out principle. It works like a real life waiting line. So the first person to call is first person to get help. We prove this with our regular queue test case, which is the FIFO.
So, in your analysis, you found a performance bottleneck with your agent list. Could you break that down for us? What does that mean in simple terms, and what would a caller actually experience because of it?
So the bottleneck is our doubly linked list for agents. We used a single list for all agents. So finding a free one requires an ON time complexity search. This means the system gets very slow as you add more agents. For the caller, this would cause a noticeable lag between an agent becoming free and the call actually being connected. So that's it.
Okay, thank you.
Do you feel this situation can realistically be adopted in real life call centers?
Yes, this can be adapted in a real life call center because it consists of all necessary features which are required for the actual call center, which are delivering call from one agent to another agent, handling a priority or a VIP call. Also, each operation in this project is very less complex, and the bottleneck it identifies in agent is just a optimization problem. The fundamental and event-driven logic and memory management makes this project a real-life application.
Thank you.
Okay.